Hello, we're back. Let's talk about stereoisomerism. Um, let's start out by defining what chirality is. When you have a molecule, an organic molecule, um, sometimes the following can take place. Notice that the positions in this molecule, one chloro, one fluoroethane, of the methyl group, the fluoro group, and the chloro group, and for that matter, the hydrogen group, are technically set in place. And if we were to look at the mirror image of this particular molecule, what we would end up drawing is the following. Notice that the fluorine here is still pointing to the back, the metal is still pointing to the front. That's because it's the mirror image. So you're to treat this segmented line as if it were a mirror, and you basically just see the reflection of this molecule. Bonds that are on the page themselves remain on the page exactly. But the interesting thing about this is that these images are technically non-superimposable, and what that really means is that if we rotate the second molecule, the mirror image, on the axis of the carbon-chlorine bond by 180 degrees, what basically will happen is that the fluorine bond that's currently pointing to the back is now going to be pointing to the front. And likewise, the methyl bond that was pointing towards us before, when we do that rotation, ends up pointing to the back. And the interesting thing is that if we were to try to take this molecule and literally place it on top of the first one, it will be impossible to do that because the fluorine no longer lines up uh, on the second molecule with that of the first. And so this is what we refer to as being non-superimposable. You cannot um, place the second molecule onto the first. And when this happens, what the molecules are basically telling you is that the initial molecule is chiral. It has a chirality center on the carbon. So the interesting thing about it is that, technically speaking, for this molecule, one chloro, one fluoroethane, there's two versions of it. The fact that the bonds can have a specific spatial arrangement is what we refer to as stereoisomerism. And I want to walk you in subsequent slides through the process of determining exactly what kind of stereoisomer we're dealing with. But before we do that, I want to kind of give you an idea of when to expect chirality and when not to expect chirality. So technically speaking, a molecule should not have mirror planes within it for you to have chirality. If there are mirror planes, do not expect the molecule to be chiral. And what that basically means is that on a molecule like this, bromomethane, um, you could draw a mirror plane that basically goes through the carbon bromine and the carbon hydrogen bond, basically this regular lines. The carbon hydrogen bond here with the bond being bold is actually sticking out of this plane, and the dash bond is also sticking out of that plane. So the fact that you can draw this mirror plane and say, well, the hydrogen on the front is basically being mirrored on the hydrogen on the back, tells you that this molecule is not going to be chiral. Same thing here. You have chlorine on the back, chlorine on the front, that are basically mirror images of each other. So you have a mirror plane in the molecule. The molecule is not chiral. By that logic, also flat molecules like alkenes are not going to give you, at least from the alkene point of view, will not give you chirality. So you should not expect alkene carbons to be chiral, or for that matter, alkyne carbons, which also flat, do not expect chirality on those carbons either. The other absence of a symmetry element is that of inversion. And that means that if you can kind of cut, well, you're not really cutting the molecule in half, but if you have the same thing on opposite ends, right? So in this case, going to the left entirely on this molecule is the same thing as going to the right. You have the same type of um, molecules or fragments. That means that you have a center of inversion. Specifically, this molecule right in the middle of the triple bond. In the trans alkene molecule right here, you also have an element of inversion right in the middle of the double bond, because we have a methyl group pointing up and to the left, and on the opposite end of the molecule we have the same thing, a methyl group pointing down and to the right. And that's what we call inversion. On the opposite ends of the molecule you have the same overall groups. So these two molecules, on top of having the alkene and the alkyne, also have the center of inversion present in it. So none of these molecules are expected to be chiral, at least, you know, in the middle of the molecule. Now, the thing that you do expect to see for a carbon to be chiral is for the carbon to be sp hybridized. So going back to the original slide here, the fact that these carbons were sp or sp2 hybridized for the alkenes and the alkynes already meant that those carbons couldn't be chiral. So it is a prerequisite that the carbon be sp3 hybridized for the most part. And what that really means is that for chirality, we're going to be looking at those tetrahedral carbons. In addition to that, all four groups that are bound to this tetrahedral carbon have to be different. And that's why 1-chloro, 1-fluoroethane qualified as a chiral compound, because this carbon right here has four different things bound to it. Alright, so to give you an example, when looking at the bond line formulas, you technically want to look for those carbons that have at least three things sticking out of it, because that has the potential for having four different groups bound to it. So starting on the carbon here, the fact that this carbon has only three bonds sticking out means that a hydrogen must be bound to that carbon. Now, at first look, you might want to say, well, that looks chiral, except that two of the groups, the ones highlighted in red, are methyls, right? So this is a methyl group, that's a methyl group. And what that means is that this carbon does not have four different things bound to it, so that's not a chiral carbon. Now, scanning the molecule further, we get to this segment, which also has three things bound to it, and that also means that a hydrogen must be bound to this carbon to complete the octet. Now, if we look carefully, we'll see that the red line here is just a methyl group, and a methyl group is different than the big things that we have on the left or right side. But if we look even more carefully, okay, that's a CH2, this is a CH2. That's a CH2, that's a CH. Right then and there we see these segments, the big segments are actually different. So altogether you have a methyl group, you have a blue segment, a pink segment, and a hydrogen bound to the same carbon, and all of them are different, so you found yourself a chiral center. Going further in the molecule towards the right, we find this other portion of the molecule where we have three things sticking out of that carbon. One of them, in addition, has to be a hydrogen to complete the octet. And we do the same analysis. We have a methyl group bound to this carbon, we have an ethyl group bound to the same carbon, a hydrogen, and then we have the big blue R group. So altogether, four different things are bound to that carbon, therefore this carbon is chiral. So we found two chiral centers present in the molecule. Okay, so another example, we can see the molecule here. Starting from the left, we'll look for that carbon that has three things sticking out of it. So that will mean that at this point, we have a potential chiral center. Okay, so we're going to examine what we actually have. The carbon, of course, has to have a hydrogen bound to it to complete this octet. So we have methyl sticking to this carbon, we have hydrogen. Those two groups are different. Then we have CH2 and then CH in the cyclopropane ring, right? And the fact that this has two hydrogens but this one only has one already means that those two segments are different from each other. And of course, those two segments are also different than hydrogen or CH3. So altogether, that carbon is chiral. Moving forward, we find this other segment that has three things sticking out of the carbon. A fourth one will have to be hydrogen, so we do the same analysis. We have hydrogen sticking out of it, then we have this cyclohexyl bound to the carbon. Those two things are different. Over here on the left side, we have a CH, and then we have a CH2. So technically speaking, you have four different things bound to this carbon. Therefore, this carbon is also chiral. Moving along, we get to this other carbon that has three things sticking out of it. A fourth one has to be hydrogen too to complete the octet. So on the one hand, we have isopropyl bound to the carbon, we have hydrogen bound to the carbon. Those two things are different. And then we get to the cyclohexane ring. So at first look, you might say, well, you have the same thing on both sides. You have CH2 and CH2 bound to the carbon. But you have to continue going along the ring to see if there's any distinction overall. So looking at the blue segment, this is a CH2, that's a CH, and then you have CH2. But looking at the pink segment, you have CH2, CH2, CH2. The entire time there's two hydrogens on each one of those carbons going, from the first carbon that's bound to the central carbon that we're analyzing, all the way to the third one. But on the blue segment, we have CH2, CH, CH2. So the fact that the second set of carbons here from the central one we're investigating um, is different on the blue segment than the pink segment means that um, these particular types of bonds are in essence different, and so this carbon is actually chiral. So you have to get into the habit of branching out further and further into your ring to make sure that nothing further down the line is gonna make a difference, because if that's the case, then your carbon could end up being chiral like it was in this case. Now, moving further into the ring, we find that this particular spot on the molecule has three things sticking out of carbon. So we investigate that particular carbon. And once again, we have to have a hydrogen bound to it to complete the octet. Fluorine and hydrogen are different, so far so good. And then we have carbon and carbon bound to the central element. So we need to now expand forward on the ring to see what's happening. So on the blue line, we have CH2. On the pink line, we have CH2 directly bound, so that's not a difference. Further down the pink line, we have another CH2, but further down the blue line, we have only a CH. So right then and there, you get a difference. Therefore, this carbon right here has four different things bound to it and is chiral. So get used to looking at these bond line structures and searching for those chiral centers, and you might have to slow down a little bit to catch the chirality center, but this is in essence what you gotta do just to determine the chirality. Okay, let's do another example right here. So I introduced some alkyne and alkene functionalities in the molecule. So by default, the sp and sp2 carbons by themselves are not going to be chiral, but that is not to say that somewhere else in the molecule they could not be chirality, right? So the fact that you have alkyne and alkenes does not negate the possibility that the molecule could still be chiral. What we do know is that on the alkyne carbons or the alkene carbons, chirality is not going to happen. But anywhere else, and notice that we have sp3, sp3, and sp3 carbons. So on those carbons, you could still have chirality. So I just want to make that distinction. Having alkene and alkyne functionalities does not negate the idea that chirality could still be present in the molecule. So we'll look at the first carbon here where three things are sticking out of it, or actually we'll look at the one right here. So three things sticking out of it. Um, what we know is that a hydrogen has to be also bound to that carbon. Hydrogen and chlorine are different, okay? Down here we have a methyl group, which is also different. And up here we have the entire blue segment that is clearly different than a methyl group. So altogether this carbon has four things bound to it. Now the carbon here on the left side also has to have a hydrogen bound to it to complete its octet. Hydrogen is different than this ethyl fragment. The ethyl fragment is different than a vinylic fragment, the one shown in red, and that vinylic fragment is different than the acetylenic fragment that we have here in blue. So altogether, this carbon also has four different things bound to it. So that's also chiral. So sp3 carbons could potentially be chiral, and not only that, but notice that this carbon here is chiral, including that alkene and alkyne functionality as part of the different groups, right? But the alkene and alkynes themselves are not chiral. So I just want to make that distinction very clear right now. Okay, in the next video, we're going to start talking about the idea of enantiomers, which are some of the subset isomers within stereoisomerism. So I'll see you in the next video.